discuss about the new data structure which is called the binary search tree. Right? So far we have discussed only the binary tree in which there was no associated with this particular kind of a tree. You can create tree in any way, just you have to take care about the property that either 0, 1 or 2 children. This is the only property which was associated with binary tree. Right? Now suppose you want to search an element on a node in a binary tree. So what would be the procedure? The procedure would be we will start from the root node, right? And then search the tree level by level. So that means if you are having this kind of a tree, right, and you want to particularly find out this particular node, you have to start from here, then go to this node, then from here you will come to this node, then this node, then this node, and then you will reach a particular node. So now in this case, the process of searching is just behave like a linear search. Okay? And the complexity of this searching is order of n that we have all. The complexity of searching is order of n, the number of elements in my list. So here, because the tree is not created by following some property except this condition that every node may have 0, 1 or 2 children, not more than that, because it's a binary tree. Right? So the searching process in case of binary tree behaves just like a linear search, and the complexity is of order of n. Now the basic objective of designing this binary search tree is to store keys in the nodes in a way so that searching, insertion and deletion can be done efficiently. So this is the only objective of designing BST. But the primary objective of this was to design a tree in which we can search an element not with the complexity of order of n but less than that. And similarly and sidewise we also can insert and delete elements from the binary tree or the tree very efficiently. So this was the objective of designing a BST. Right? Now the BST, there is a property in case of binary search tree. There is a property, and that property is for every node x, right? For every node x, all the keys in the left subtree are smaller than the key, and all the keys on the right subtree are larger than the key value in x. Now suppose this is my node x. All the values which are here on this left side of this, they are smaller than this, and all the values which are there on the right side of this, they are greater than this. Right? So these are greater elements. These are the elements which are greater than this node, particular node, and these are the elements which are smaller than this node. So this property is again iterative. That means it will hold for every node. Suppose you are at this particular point, right? At this point x. Now this node should be less than this, and this node should be greater than this. Now if you reach at y, suppose at this particular point, now this node should be less than this, and this node should be greater than this. Right? So this property of binary search tree. Now in the previous case, there was no property associated while creating. That's why I have given you one program to create a binary tree. In that case, you have to just take care about this property that it should not, a node cannot have a more than 2 children. That's it. But here, whenever you are creating a node, you have to find out where to fit that node. Because for binary search tree, you have to take care about this property. Right? So that for every node, all the keys in the left subtree. So whatever the keys in this left subtree are, they should be smaller than this, and the nodes which are on the right side of this tree must be greater than this. Fine? Is it clear? Now here we are assuming that all the nodes are distinct. That means there is no repetition of node. Right? So if there is a repetition of node, if the tree is allowed in such a way that there is a repetition of node, then this definition, this property would be changed. Right? So the only change would be the keys in the left subtree are smaller than the key in X, and the keys in the right subtree are larger than and equal to, right? Larger than or equal to. Okay? Every node on the right subtree of the n of the x. Clear? Is it clear to everyone? The change that we will bring brought in while the nodes are not distinct. So if the nodes are distinct, that means there is no repetition of nodes in the tree. In that case, this property will hold. But if there is a repetition in the tree, then we can say greater than or equal to the every node the greater than or equal to the node x. Right? So that is the change that will be brought in when there is a repetition of nodes. But in application, in practicality, such kind of conditions are not there because most of the records, they are distinct. Fine. So we would not face such kind of situation. Now let's just take this example of binary search tree. Here we have a node 40. Fine. Now if you notice the left, all the nodes on the left part of this are smaller and all the nodes on the right side of this are greater, right, or larger than 40. So this is a binary search tree. Now if I move into the tree, in the interior of the tree, now if you notice this portion, all the nodes on this part of this 15, because 15 is a root node for this particular tree, they are smaller, and all the nodes on the right side of this, they are larger. Now if I move from here to here, see here also all the nodes on the left side of 68, because 68 is a root node for this particular tree, are smaller, and all the nodes here are larger. Now if I further go down into the tree, and if this is my root node, 11 is my root node, then this is the node which is on the left side of 11, which is smaller, and this is on the right side, which is larger. Here also there is no left child, but there is a right child which is greater than 41. Here there is no left right child, but there is a left child which is smaller than 92. So the definition of binary search tree, or the property of binary search tree, it will hold, excuse me, it will hold for every node in the tree. Fine. Is it clear? Is it clear to everyone the difference between the binary tree and the binary search tree? Now you cannot create a binary search tree randomly. You have to follow this property. We will see one example how we will create binary search tree by taking some random numbers. But in case of binary tree, there was no property associated with it. So you can create a binary tree very easily. But in case of binary search tree, you have to follow this property. Fine. So here also then all the nodes are distinct. And there is no repetition of the node. Right? Now the advantage of this kind of tree is the average running time of to search an element in BST is order of log n. Why it is less as compared to this complexity? Because if you notice at this particular point, my tree is divided into two halves, right? Because all the nodes on this side are larger, all the nodes on this side are smaller. Fine. So it uses the divide and conquer strategy. Right? It uses this strategy for searching. Because when you are at a particular point, and if you compare this your item that you would like to search with this particular node, with this root node, if it is smaller than this, there is no chance that it will appear in this part of the tree. Right? So you can simply discard this portion while searching. Similarly, when you reach at this particular point, suppose after getting to this, you reach at this point and the node you want to search is greater than this. So you can easily discard the nodes which are on the left of this 15. So it may not it will not exist in this portion because it is greater than 15. So it may appear, it may come in this portion of the tree. Fine. So accordingly, that's why the complexity of searching, or the in case of binary search tree, has been improved with respect to this complexity, or the running time with respect to this complexity order of log of n. Whereas in the binary tree it was order of n. Now if I compare this complexity with the sorted linear array, fine, if I compare it with the sorted linear array, then which algorithm you will apply? If you remember, linear search or binary search? If the
Binary.
elements which, yes, you will apply binary search, and the complexity of the searching is order of log n. But in case of sorted linear array, insertion and deletion is difficult. It is a time consuming process that we have already discussed. Insertion and deletion is time consuming. Right? So this is the case of binary sorted linear array. We can apply binary search, and the complexity of searching that particular element by using the binary search is order of log n, but insertion and deletion is time consuming. And if I compare with another data structure which is called linked list. Now in case of linked list, insertion and deletion is easier. It is easier, but searching is again linear. Take order of n to search an element in the linked list. So if I compare the binary search tree with these two data structure, which is the linear array, and the algorithm that we will apply on the linear array is the binary search, complexity, no doubt it comes out to be order of log n, but insertion and deletion are time consuming. If I compare it with the linear search linked list, in that case, insertion and deletion is easier to implement, but searching is again linear, which is order of n. Right. So this algorithm is this BST is that particular kind of a data structure in which searching is also improved, as well as insertion and deletion is also improved. Fine, because if you want to search a particular if you want to insert a particular element in this tree, fine, and suppose let's say you want to insert 50 in this tree. So what would happen? You will compare this with this particular node, and what is the result of this? This half portion of your tree will be discarded because this 50 cannot exist in this portion. It will fall in the right side of the tree, not on the left side of tree, because 50 is greater than 40. So that means with the insertion operation also you are reducing the insertion domain. Right, because आप यहाँ पे हैं, if you are at this point, you compare with this. Now you are 100% sure that 50 will not appear in this portion. It will not come in this portion. So all the nodes which are there is no need to search for where to insert this 50. Automatically it will come in the right side of the 40, not on the left side, because there is a property associated with the binary search tree. So that's why the complexity of this insertion is also close to order of log n. Right? So this is the tree, this is the data structure which gives you the flexibility of insertion, efficiently inserting an element into the data structure, efficiently deleting an element from the data structure, as well as searching in a time consuming manner. Right? So now let us discuss the searching, and this is the operation that we will discuss now, which is the searching and insertion operation in BST. Now these two operations can be combined together. Why? Because in case of searching, we have to find the location. So the purpose of searching
सर,
is,
मेरे को आपसे क्वेश्चन पूछना था
जी जी,
कि जो हमने एल्गोरिथम्स लिखे हुए ट्रावर्सल के, वो हमने आइटरेटिव भी लिखने हैं कि हम रिकर्सिव भी लिख सकते हैं?
लिख सकते हैं, कोई इशू नहीं, लिख सकते हैं, ठीक है। हेलो,
हाँ जी सर,
हाँ लिख सकते हो,
वो
नो इश्यूज।
रिकर्सिव इजी है, आइटरेटिव
यस
थोड़े
यस यस, रिकर्सिव इज
डिफिकल्ट
इजियर।
लगते
सो
हैं, रिकर्सिव
मैंने
इजी है।
जब मैंने आपको प्रोग्राम दिया था, मैंने कुछ नहीं बोला आपको करने के लिए, आप जैसे मर्जी उसको इम्प्लीमेंट करिए, बिकॉज नाउ यू हैव दैट आइडिया विच टाइप ऑफ एल्गोरिथम यू विल राइट एंड विच इज बेटर देन द another one. So you can write recursive also, no issues, right?
ओके, थैंक यू सर।
Okay, so the searching operation is we have to find the location of an item in the tree. Now the insertion operation is we want to insert a node, a new node or the new item in the tree, in the BST. Now inserting a new item in the tree, we have to find out its location. Have to find out its location. Right? Now, if I consider this tree, if you want to insert this 50 into this tree, you cannot insert 50 here. If you insert 50 here, this would violates the property of the BST. So that means before inserting 50 into this tree, you have to find out what would be the location of this 50 in my tree. Fine. So that's why these two operations, they are combined together, because if you want to implement insertion, you have to implement the searching also to find out its location, because you have to find out its location in the BST. Its location in the BST first, then only you can insert. Right, so this is the process. So what we will do here in the case of searching and insertion, suppose an item is given to you, you want to insert this item into the tree. Fine. So the first thing is you will compare your item, the given item with, here if you see, if this is my item, what I am doing, I'm comparing 50 with my root node. So compare item with root of the tree. Right? Now there are two chances. One, the item, it may be less than this or it may be greater than this. If it is, now compare item with the root of the list. Now there are one case would be if item is less than root. If it is less than root, then proceed down to this portion here in this portion. If it is greater than, proceed down to the rightmost portion. So if item is less than root, then proceed towards left child of root. Is it clear to everyone? Now the searching and the insertion is what? First we have to compare our item with the root node. If the item is smaller than the root node, proceed down to the left child. If item is greater than root, then proceed towards the right child of root. So this is my initialization, where to move, because when I reach at this point, you have to decide either I have to move to this side or to this side. So as I discussed in the introductory lectures, that there is a decision making where to move in case of trees, whether I have to move to left side or to the right side. So here you have to decide which path you have to follow so that you could search the location of this item in the tree. Fine. Now the second step of this is repeat repeat this step until number 1. Now when I reach at this point, I compared my item with this 40. Now it is greater than this, so I will move here. My pointer will come here. Now at this point again I will compare this with this. So my pointer, now here in this case earlier it was greater than 40, so I moved on the right side. Now if I compare 50 with 68, now it is smaller than this. So I will proceed down leftmost path and I will reach at this 50. Is it clear? So now until अब दो केसेस क्या हो सकते हैं? One case could be you reach at a point where item is equal to some n, which shows where n is that item which is equals to n, which shows that the item you are searching is already there in the list. So your search is successful. Now the second case is your search is unsuccessful. That means the item that you are seeking for in the tree does not exist in the tree. Now, if it does not exist, that means you want to insert it. So insert element in the tree. Now, if I stop at this point, let me change at this point, where the problem which is given to you is to find the location of an element or the item in the binary search tree. You will go on repeating this process, and if you reach at the second point of the B step, you say search is successful, unsuccessful, that means item is not in the list. Now, if it is a insertion operation, then you will also follow this process, and if search is unsuccessful, you will insert that element in the tree. Or there may be chance that the item is already there in the list, in the tree. So if you are allowing duplicate elements into the tree, then you can insert this element on the right side of that particular node. If you are not allowing the redundant elements or the duplicate elements in the tree, you can say element already exists. Fine. So it all depends upon which the property of the tree, whether you are allowing the distinct elements only or the non-distinct elements also. Fine. So if you allow only the distinct element or the unique elements, then you can say element already exists if this condition is fulfilled and you are performing the insertion operation. Right. But if you are if your tree is non-distinct and item is already there on in the list, you can insert on the right side of that particular node. Right. So this way you can insert elements into the tree. Right. So let's see one example of this, how we will search a particular element in the tree. Now suppose you want to search element 18. Right. So once we will compare this with this. Now this is smaller than this, so we will move to this. We will compare this with this. We will move to this. We will compare this with this. We will move to this, and we will compare this with this, and the items are equal. So it is a successful search. Fine. So if you want to, the second element that you would like to search is, let's say it is 95. Fine. So I will change the color. So the second element is 95. You will compare this with this. It is greater than this. So we will move to this portion. It is again now it is again greater than this. So we will move to this portion, but there is no element. So we will say here there is no element, no right child, or you can say right child. The search is unsuccessful search. This is how we will search element in a BST, and you can see approximately there are 10 elements in the tree, and the number of comparisons you are doing for searching this element is almost 3. 1, 2, and 3. These are 3 comparisons are required to say whether this element exists in the tree or not. Fine. So this way, that's why the complexity of searching this in this the BST is order of log n, because we are dividing my search space by half. Fine, because at particular every comparison we are discarding some number of nodes from the tree. Okay, so now if it is now in this case I'm searching 95. If I want to insert 95 into the tree, then the location of 95 would be this one. Fine. So in case of insertion, you have to search first and then you can insert. Fine. So we will write two algorithms for this insertion operation. One is to find out which would basically fulfill our requirement of searching operation, and the second is insertion, which will basically give you the find as well as insert. So first we have to see how we will insert search in a BST. So let us write down see one example of creating a BST. Right? So suppose these are the nodes which are given to you. Here also all the nodes are distinct. Right? So first node which is there is the 40. So we will insert 40 as it is. Right? So this is the first node because root is equals to null. In this case, root is equals to null because there was no tree. So the node which you are going to insert in the tree is going to be the first node. So it becomes root node. Now after that, the next node is 40 is already there. So the next node is 60. Now 60 is again, because it's a searching and insertion, you have to see where to fit 60. In this case, 60 is greater than this. So 60 will go on the right side of this. Now next is 40 and 60 already there. So the next node is 50. Now again you have to start from the root node. Don't start from here. Start from the root node. Fine. Every time when you are inserting a new node into the tree, you have to start from the root node. Now here 50 is greater than 40. So you will reach here. 50 is smaller than 60. So it will go here. Fine. So the next let me complete this. All right, so the next node is 33. Now here again start from this particular node, root node. 33 is smaller than 40. So that means 60, 50 and 33. यहाँ पे 33 आपने किया था. This is 50. This is 60. Fine. So after this, the next node is 55 and my tree is 40, 33. This is again a very important question from examination point of view. आपको number दिए होंगे, you have to create a BST out of that. So the next node is 55. Now again you have to compare 55 from the root node. 55 is greater than this. It will reach here. 55 is smaller than this. So it will go here. 55 is greater than this. So this node will go on the right of this node. So the next is 11. Now 11 again you will compare. Let me draw this tree first. Now you will compare 11 with this 40. Now 11 is smaller than this. Fine. It is smaller than this. So you will go to this point. Now it is again smaller than this. So you will go to this point and 11 will be inserted here. So now this is the final tree, which is BST. Now if you see, if you want to verify whether it is a BST or not, now you just have to see all the nodes on the left side of this. All the nodes on the left side of this, they are smaller than 40. And if you see the nodes which are on this portion, on this side, they are greater than 40, right? And if you see for another node, if you want to verify for some other node, let's say 60, all the nodes on the left side of 60 are smaller and there is no right side. And if you want to verify for the 33, all the nodes on the left side are smaller and on the right side there is no node. So this is my correct BST which we have created, right? So this is the correct BST tree. Any doubt to anybody you can ask up to this point. If you have any doubt, we can discuss. This is how we will create a binary tree or binary search tree. One thing you have to take care, whenever you are inserting a new node, always start from the root. Don't think कि आपने 60 insert कर दिया, now the 50, you have to just compare 50 with 60. You have to start from here, right? Because if it is a 33, then it would go here, right? अगर 50 का जो sequence होता 40, 60, then 33 will come. Then the 33 will go on the left of 40. So you have to always start from the root node. Compare your element with the root node and then see where to, and just follow this process. You just have to follow this process. Compare item with the root of the tree. If it is on the if item is left side, if less than root, then proceed to the left side. If it is greater than root, then proceed to the right side. And this process will go on because the root here means every node is a root. Right? Here also it is a root. This is also a root. 33 also a root. Right? When you reach that, again compare item with the see where to move left or right, where to insert this particular node. So any doubt up to this point to anybody? I can repeat it again.
Yes sir.
Yes.
सर अगर एक न्यू एलिमेंट सर इंसर्ट करना है सर 22, तो सर वो 11 के राइट में आएगा?
ये देखो 22 डाल दिया हमने, फाइन।
यस सर।
ठीक है, मैं इसको दोबारा बना लेता हूँ बिकॉज वहां पे मैंने कुछ एडिटिंग करी है. सो दिस इज द ट्री विच इज ऑलरेडी देयर. 60, 50 एंड 55. तो ये मेरा ट्री था, फाइन. नाउ देयर इज अ न्यू नोड 22. नाउ फर्स्ट यू हैव टू स्टार्ट फ्रॉम द रूट नोड. क्लियर?
यस सर.
Whenever there is a new item, start from the root node. Now 22 is
smaller than 40.
So where to move?
Left of root node.
Left of this. So when I reach that, again compare your item with 33.
Yes.
So it is again
smaller than 33.
So it will come here. So again I compare it with 11.
Now greater than 11.
Here.
Okay sir. Thank you sir.
So any doubt to anybody? You can take any node. अब यहाँ पे मैंने यहाँ तक चल लिया है. We can take a bigger node also. Let's say 80. हमने 80 ले लिया. अब we started from here. We will always start from the root node. So we will start from this 40. 80 is greater than 40. We will move here. 80 is greater than 60. So where to insert this? At this point. Take another node. Let's say 48. Right? 48. So we will start from this root node. It is greater than this. We will reach at 60. It is smaller than this. We will reach at 50. It is again smaller than this. So we will insert 48 on the left of 50. Right? So this again is a complete, it's a BST, because if you notice on the left side of 40, all nodes are smaller. On the right side of 40, all nodes are greater than 40, which is X. ये जो हमने definition property देखी थी, X, node X. So all the nodes on this node X, on the left side of this node X are smaller. All the nodes which are on the right side of this node X are greater. If this is my X, all the nodes on my left side of this X are smaller. All the nodes on my right side are greater. And if this is my X, all the node on the left side are smaller and there is no right side. Right? So this way you can verify whether the tree that you have created from some random number of elements is a BST or not. Clear? I think up to this point, it is clear to everyone.
सर एक डाउट है सर को।
हाँ जी पूछो जी।
सर अगर जैसे सर 33 ऑलरेडी एग्जिस्टेड है तो सर अगर कोई सर 33 अगर कोई दोबारा एंटर करता है तो सर फिर वो कहाँ पे इंसर्ट होगा?
अभी मैंने ये क्या बताया था, ये देखो, राइट सब ट्री आर लार्जर और इक्वल।
ओके सर।
वो उसके
ओके
राइट साइड में चलता है।
ओके सर, थैंक यू सर।
वैसे ये आता नहीं है क्वेश्चन में, क्योंकि it is always recommended that the tree BST all the nodes should be distinct.
ओके सर।
ये तो सिर्फ मॉडिफिकेशन के लिए, इट्स मॉडिफाइड डेफिनेशन बेसिकली, कि अगर इक्वल आ जाए तो उसको हम राइट साइड में डालते हैं।
ओके सर।
Let's see the algorithm of searching. So in case of searching operation, find LOC. Now the various parameters that we will pass to this is info, left, right, and root. These are the parameters which are required, because आपकी node 3 parts में divide होती है, info, left and right, and there is a root pointer variable. And if it is a searching operation, you also require this item that you want to search in the tree, and this LOC, which is the location of this item, and PAR, which is the location of the parent of this item. So location LOC, it stores the location of the item, and PER, it will store the location of the parent of LOC. So why this is required, I will discuss later on, because I think it will help you to basically insert element into the list. If it is a searching only, then up to this point it is over. But here we are combining these two operations together, finding and searching and insertion. So find location, what it will do, it will find out the location of the item as well as the location of the parent of that item, so that we can insert. Now there could be few cases, special cases that would exist in this searching operation. First is if tree is empty. How to find out tree is empty? If root is equals to null. If this is the condition, then what would be the value of LOC? It is also null. And what would be the value of PAR? It is also null. अगर ट्री नहीं होगा तो ना लोकेशन होगी एटम की, तो ना ही उसका पेरेंट होगा. स्पेशल के सेकंड क्या हो सकता है? Item is at root, or root is equals to item. The item that you want to search, you are able to find out at the root node of that particular item. So in that case, location is equals to root, but the location of parent is equals to null. Fine. Now in this case, the third case is item does not exist in the tree. Fine. So that means location is equals to null. ठीक है, but parent is not equals to null. This is third condition. Now if you see this example here, see I want to search this 95, right? So 95 does not exist in this tree, but there is a parent of 95 also, which is this, which is not null. So that means if I want to insert this 95 in my tree, I would require this parent, so that I can insert 95 as a right child of this parent. Right? So this is the condition for that. And if this is the condition and item does not exist in the tree, or the location is equals to null and parent is not equals to null, insert element at parent. Right? So this is the modification, this in the searching and insertion operation, because finding up to this point, it is finding out the location of the node, whether it is null or it is at the root or it is null, fine. But if you want to insert that node into the tree, then location is equals to null, then the role of parent will come, because the node that is not there in the tree that you want to insert, you will insert as a left or right child of this parent node. So insert element at parent. Where to insert that we will see later on, how to insert that. Fine. So these are the basic special cases of your algorithm. These are the special cases. I think you can easily recognize the various steps that are required for searching. Now, the first step is you will check whether tree is empty or not. So this would be the first statement of your algorithm. If root is equals to null, then set location is equals to null parent and return. If item is, then the second is you are checking whether the item is at the root or not. If item is at the root or not, that again you can check if item is equals to info of root, because root is a pointer variable which contains address. It contains address. So info of root will give you the item that is there in the node. Right? So you will compare your item with info of root to find out this. If it is not, if these two conditions are not fulfilled, then you will move to the third case, and then there are few steps for initialization in the third case. So that we will discuss in the next class. Right? Okay. Thank you very much. I'm going to end this.